Hey everybody, it's Mrs. Harbin. Welcome to video notes about equilibrium. Make sure you know these 4 things. Alright, so chapter 18, section 18.2 is all about equilibrium. You'll love it. Alright, so here we go. What makes a reaction go? Well, we know that increased entropy, positive delta S, and decreased enthalpy, negative delta H, make a negative delta G. But what about these cases? So you've got solid, gas goes to solid, that's negative S. But look, it's positive H. I'm sorry, negative H. So we got negative H and negative S. So we don't know. We'd have to calculate G. What about this one? Okay, so basically, nature favors this way for heat, but nature favors that way for entropy. Okay, what about this? Solid, gas, go to gas. Wow, yeah. But it's endothermic. So positive S, positive H. So really what's going on is nature favors forward reaction for S, but reverse reaction for heat. All right, so what do we call that? So 3 possible results. If delta G is negative, we know it's spontaneous. So that means the reactants turn into product. Woohoo! If delta G is positive, that means the reverse reaction is favored or spontaneous. But if delta G is equal to 0, then we can get equilibrium, which means the forward reaction happens and the reverse, because maybe entropy is pushing one way, but enthalpy is pushing another. So we get this thing called equilibrium. Equilibrium. What is equal at equilibrium? Only one and one thing only. The rate of the forward and the reverse reaction are equal. So if the cars are going this way, the same rate as the cars are going that way, then you have the same number of cars on this side. So say we had 300 cars on this side to start with, but the same number go there as go there, and we had 200 cars on this side to start with. If they're changing at the same rate, then we still have 200 here no matter what, and 300 there no matter what. Okay, if you have your iced tea, I love iced tea, and you got sugar on the bottom that's not dissolved, technically, some of the dissolved sugar is precipitating at the same rate that some of the solid sugar is dissolving. It's called the equilibrium. Okay, so what does dynamic equilibrium mean? Equilibrium is dynamic. Dynamic means change. So what does dynamic mean? Dynamic means change. So at equilibrium, there's change going on, and that change never stops. But what's cool about the change is the amount of change that's caused by this equals the amount of change that's caused by that. So it looks like the water level doesn't change, but it's new water. All these new water molecules are coming in. All of those old water molecules are coming out. So the water molecules are different, new ones, old ones, but the amount of water in there doesn't change. But it's always different water molecules. So what's changing at equilibrium? The rate. The forward stuff is changing into the reverse stuff, but what's not changing is the amount. What is changing is the rate. I'm sorry. Yeah, I am so messing this up, but I'll get back on now. Anyway, equilibrium means that there's constant change going on, but the rate going in equals the rate going out, and so the rate is equal. All right? So there's this principle about equilibrium called Le Chatelier's principle. And so here's what it states. If you change a system that's already in equilibrium, it's going to shift to get back or to reduce the effect of that change. Okay, so if you stress out an equilibrium system, it's going to shift to reduce that stress. How can we stress out an equilibrium system? Well, we could add something to it, or we could remove something from it. We could add something to it, like a reactant or a product. We can remove something by doing a chemical reaction. Okay, we can change the temperature of the reaction, which, when you're changing the temperature, it's because you're adding or removing heat. All right, change the temperature by adding or removing heat, or you can change the pressure of the system. Okay, so let's see what that means. Hey, look, it's a chemical reaction. So delta H is negative. So what does that mean? That means that it would be on this side, 92 kilojoules. Right? So look, delta H favors the forward reaction because it's negative, but delta S favors the reverse reaction. So what if we increase pressure? Well, we'd be causing stress on the system. Which side would feel the stress? Well, the side with more gas particles. So we have 4 gases on this side, we have 2 gases on this side. So the side that feels pressure increase is this side. They're like, oh, hey, we're getting closer together, or there's more pressure on us, so we're going to shift away. So shift in the position of the equilibrium is towards products, or shift right, because more gas shifts away. Shifts away. When you increase pressure stresses out the more gas, so it shifts away. What if I increase the temperature? Well, it's like adding more heat. So here's the heat on the product side, so it's going to shift away from the stress. So the shift in position of the equilibrium is towards reactants, away from the stress. Hey, what do you do when you're stressed? You want to relieve stress. So increased temperature shifts away from heat, because adding heat shifts away from heat. Decrease in hydrogen. Alright, so what if I started to take some of this out of the reaction? Okay, well, that puts stress on this side to push towards that side. Okay, so if I take some of this out, it's like leaving a big hole right here. What do you do if there's a hole? You fill it up. Okay, shift in position of equilibrium shifts toward or towards reactants. Okay, why? Remove reactant, shift to fill. Alright, increase in concentration of ammonia. Well, first of all, we gotta know what ammonia is. Oh, look, this is ammonia. So if we all of a sudden in this reaction have more ammonia, then it would put stress on this side, so it's going to shift away from the stress. So shift towards reactants. Okay, because increase product means shift away from the products. Alright, decrease in temperature. That means we're going to cool it down, removing heat to decrease the temperature. So if I take this out, bye-bye, and I leave a hole over here. So then it's going to shift towards heat, towards products, to the left, to the right, I mean. Okay, so decreased temperature means shift towards heat. Shift towards heat. Okay, so we'll keep practicing. Now, what does it mean to stress it out? So we talked about adding a reactant. Too much reactant, shift towards product to reduce the reactant. Right? So all of a sudden on the left, so reactants turn into products, products turn back into reactant. If we add more of this, we bump up the rate of this side because there's going to be more collisions, so the equilibrium will shift towards the other side. What if we remove a reactant? Okay, take it out. Well, if we remove a reactant, it can't collide because it's not there, so then the products start to make more reactant, so it shifts towards the reactant. Okay, so I kind of like when you remove one of the things on either side of the arrows, it leaves a big hole. What do we do when we have a hole? We can fill it up. All right, you shift to fill up a hole. All right, pressure. What is pressure? Pressure, well, only affects gases in an equilibrium system. So if you increase the pressure, pressure goes up, then the side with more gas feels stressed out. All right, so it's going to shift towards the side with less gas. But if you decrease the pressure, then you give the side with more gas a relief. All right, decreasing pressure relieves the side with more gas, so it'll shift towards the side with more gas. All right, what if you add or remove heat? Well, treat heat as a reactant or product. If it's on the left side, positive left endo. Right? If you add heat to a reaction, it's going to shift away from the side with heat. If you remove heat, it leaves a hole, so it's going to shift to the side with the hole. And those are your favorite characters from our favorite movie. Hi, guys. All right. So, oh, look, it's another balanced equation. And look, it's an equilibrium because look at the double-headed arrow. And look, delta H is negative. So we have heat on this side. All right. What if we decrease pressure? Well, pressure affects gas particles. Decreasing pressure means that these 9 gas particles on this side and the 10 gas particles on this side, decrease in pressure favors the side with more gas because then it has more room to spread out. So it's going to go that way. All right, shift right. Shift right. Okay, increase temperature means add heat. Adding heat means stress out this side, shift left. Shift left. Decrease amount of oxygen. Here's oxygen. If we take it away, leaves a big hole, shift left to fill that hole. Increase the concentration of ammonia and oxygen. More of this and more of this. Stressed out. Shift away. So it's going to shift right to relieve the stress. Okay, increase concentration of carbon monoxide in water. I said carbon monoxide. I said carbon monoxide, but it's nitrogen monoxide. So increase this and increase this. More of this, like, shift away. So it's going to shift left to decrease that stress. All right, a little more practice. Let's put it all together. So here's a balanced equation. Predict the shift if more carbon dioxide is added. So if we add more of this, it's going to shift away. So shift left, away from the stress. If we add heat, okay, add heat. It's going to stress out the side with the heat. Okay, puts more stress on this side. Actually causes this side of the reaction to go faster. So it's going to shift right. All right, keep going. Is there more? Whoa, look how pretty. So here's a balanced equation. All right, here's a beaker of regular water, a beaker of ice water. Okay, so if you look at this and see that it's ice water, okay, so how did we get ice water? We cooled down the reaction. Which way did the reaction shift when we cooled it down? Well, it shifted towards the pink side. So this is reactant side favored right now. How do I know? Look, it's pink and the reactants are pink. All right. This is products favored. How do I know? Because products are blue and this is blue. So what's this? If we make it colder, it's shifted towards pink. All right. If it shifts towards pink when it's cold, what do we do when it's cold? Is we remove heat. So heat must be a reactant, and removing the heat causes it to shift towards the side with the heat because it's removing heat. So color changes in an equilibrium system help us decide which way the reactant shifted. If I take a reaction that's blue, this reaction that's blue, and I remove the heat, it turns pink. That means it shifted towards the pink. Wow, that was super duper fun. So let's review. Okay, equilibrium is abbreviation for EQ is abbreviation for equilibrium. Equilibrium is dynamic. That means rate of change of that equals the rate of change of that. Equal rates for equilibrium. Le Chatelier's principle says if you stress out a system, it's going to shift to relieve stress, just like you shift to relieve stress. You use stress relief. Maybe you do deep breaths or something. If you add or remove stuff, the equilibrium's constant. So if you add stuff, it shifts away. If you remove stuff, it shifts towards. Okay. Pressure. Equilibrium is constant. So if you change the pressure, you're going to change it. We'll talk about volume another time. If you change heat, all right, if you change the heat, you don't need to know about this K stuff, but if you change the heat, it's just like adding or removing a product, so it's going to shift the equilibrium. Anyway, hope you enjoy this. It's going to be a quick week. Hope you guys had a great break. Peace out. Hey, look, it's Pop-Eyed Cow, and he says you should read chapter 18, section 18 too, so you better. Peace out. Okay. Oh, hey, it's objectives again. 4 things, 4 days, we got this. Okay, read them. And then I'll put them up so to see if we got them. All right, really now, bye.